Exercise 833 is again trying to ease us into drawing these complicated E1 mechanisms. Now in E1 mechanisms, you will always have loss of a leaving group and always have proton transfer. Those are just the staples, things that have to happen in order to have an E1 mechanism done, even in order to get the reaction to happen at all. You have to remove the leaving group, and you have to remove a neighboring hydrogen so its electrons can replace the electrons that the leaving group took with it. Now, in the previous exercise, we saw how to decide when to do a proton transfer using acid. In that previous video, we did that. In this video, this is meant for some practice in recognizing when you need to do carbocation rearrangements. So the procedure here is take your molecule and redraw it, but replace the leaving group with a positive charge. Because when the leaving group leaves, that's the carbocation that you would be left with. Now, ask yourself, will that carbocation rearrange? What type of a carbocation is it? This is bonded to, let me make this a little brighter, this is bonded to 1, 2, 3 carbons. So that is a tertiary carbocation. Next door, this carbon is just bonded to 1, so it's primary, and that's the same for these others. These carbons are each just bonded to 1 carbon, so they're both primary. So the carbocation is already on the most substituted, and therefore the most stable position. It's already on the most stable position nearby, and so there's no carbocation. You won't have carbocation rearrangement if you do an E1 reaction with that molecule. Okay, let's go through the same procedure with B. We're going to redraw the same molecule, but instead of our leaving group, and here we have a bad leaving group, that's a sign that we're going to have to do a proton transfer in the beginning by adding acid, but let's say the leaving group leaves, we're left with this carbocation. So we replace the leaving group with a positive charge. What type of a carbocation is this? The carbon with the positive charge is bonded to 2 other carbons, so it's secondary. Next door, the carbon is also bonded to 2 carbons, so that is also secondary. Above, it's bonded to 1, 2, 3, 4 other carbons. Now there's no room there right now to have a carbocation. But if one of those methyl groups took its electrons and moved over, then you would have a slightly different looking carbon skeleton, but the carbon that's missing electrons now is this top one, and so the carbocation would have been shifted. If it shifts that way, this new carbon is bonded to 1, 2, 3 other carbons, and so the carbocation would be tertiary. Now notice, this is a more stable position. And because this carbocation rearrangement produces a more stable carbocation, there is carbocation rearrangement on this molecule. So ultimately, the double bond will be focused around that carbon there, with a very different carbon skeleton, rather than around the one you would have expected at first. Okay, same process of thought with C. Redraw the molecule, but instead of your leaving group, and here we have a bad leaving group, so we'll have to do a proton transfer by adding some acid, but instead of that leaving group, once it leaves, after we add the acid, draw a positive charge. That'll be the carbocation that's still there right after the leaving group leaves. And ask yourself, what type of a carbocation is that? That carbon is bonded to 1, 2 other carbons, so it is secondary. The carbon below it is also bonded to 2 other carbons, so it is also secondary. The carbon above is bonded to 1, 2, 3 other carbons, and so it is tertiary. The tertiary carbon is a more stable position for a carbocation to be on, so you're going to draw a carbocation rearrangement. Now notice, just like above, you never draw an arrow showing the positive charge moving. The curved arrows show the movement of electrons. You want the lightest species to move. And the lightest species here is the implied hydrogen. So that can take its electrons and move over to the positive charge. And now, with this hydrogen over here, the carbon that's missing electrons is this top one, and we have our tertiary carbocation. So because there is a more stable position for the carbocation to be on nearby, there is carbocation rearrangement in this exercise, if you try to do an E1 reaction with this molecule. If you go through the same thought process for D, you'll redraw that molecule, but replace your leaving group, and note that right now it's a bad leaving group, so we'd have to do a proton transfer by adding an acid so that could leave. But once it leaves, we have this carbocation. What type of a carbocation is it? The carbon that it's on is bonded to two other carbons, so it is secondary. The carbon below it, also bonded to two other carbons, so it is also secondary. The carbon above it, bonded to two carbons, so it is also secondary. So none of the other positions is more stable than the one that it's already on. They're all the same, they all have the same stability, but it takes energy to move electrons over, so there's no driving force to make that happen. And so because there is not a more stable place, there's not a more stable atom next door where the carbocation can move, it does not move. And in this case, there is no carbocation rearrangement. If we try to think through E, we'll go through the same procedure. We redraw the molecule, but instead of the leaving group where it was, we just draw a positive charge. So it was on this carbon, that's this one here, that's where I'm drawing the positive charge. What type of a carbocation is that? That carbon is bonded to 1, 2, 3 other carbons. So this is a tertiary carbocation. Next door below, it's primary, it's only bonded to 1. To the right, it's bonded to 2, so that's secondary. To the left, this carbon is bonded to 2 other carbons, so it is also secondary. So the most stable position for the carbocation to be on is that tertiary position. So because that's already there, there is no carbocation rearrangement for this molecule. If this molecule undergoes an E1 reaction, the carbocation would not rearrange. And last we have F. So we're going to redraw the molecule, just instead of the leaving group, we're going to draw a positive charge. After the leaving group leaves, it takes its electrons, and the molecule that's left, the carbon chain that's left, is missing those electrons. The carbon that's missing the electrons has a positive charge. So once you have that, ask yourself, what type of carbocation is that? That carbon is bonded to 2 other carbons, so it is secondary. The carbon below it, also bonded to 2 other carbons, so it's secondary. The carbon above it, also bonded to 2 other carbons, so it is also secondary. So the carbocation is already on the most stable position it could be on, so it doesn't have any reason to move, and there is no carbocation rearrangement for this molecule. So hopefully this gives you a little bit extra exercise in watching out for this middle step. So now we've seen all of these steps. We've done previous practice with showing loss of a leaving group and proton transfers separately. We did it in the previous problem. We practiced recognizing when you'd have to add an acid to do that proton transfer. And in this video, we did some practice in recognizing these carbocations. So next time, we're going to start, in the next video, we're going to put all of that together and draw a complete, more complicated